Copyright in these lectures is either owned by the ANU or a third party who has licensed the ANU to use it. Students may use the recording for personal study only. No lecture may be communicated online, copied or shared without the prior permission of the ANU.
Okay, let's make a start. So, I've put a couple of new links live on the interesting links part of the Waddle page. So something fun to look at. We'll have a look at one of them today. We were going to look at both of them, but I think it's finally come to life. So the links I put up are links to a website called Information is Beautiful, which is a title of a book by a guy named Ted McCandless, who has compiled weird and wonderful visualisations of all kinds. So we'll have a quick look at that. There's a TED talk that he gave as well if you want to watch that. We won't watch it here, but you can watch it at home. And the other one I'm going to show you is a web page that's put together by a guy named Michael Friendly at the University of York in Canada, called the Gallery of Data Visualisation. And I'm going to show you a particular couple of examples out of that page, a couple of which come from Tufte's book, but one which is widely regarded, and you can be the judge, as the best graphic of all time. So we'll see if it lives up to that billing. So we'll start with Information is Beautiful. So this is a book by David McCandless, and it's a pretty snazzy looking book, and it covers all manner of visualizations. Okay. Like most people who write books that sort of make the bestsellers list, he's out on the road now earning money by giving talks and so on. I like to fantasise this is what I could do if I wasn't teaching statistics at the ANU, but probably not. But anyway, so all sorts of stuff here. So basically there's links to all of these different graphics, and you can see they're all pretty, I don't know, silly in some way, sort of slice of life stuff. Take a particular topic and find a graphic on it. The graphics are all genuinely bad in the sense that I think in a lot of cases they make information hard to get. And of course that's the whole point of that first part of that project we're doing, is to look at graphics that are out there and to sort of critique them and say, well, what's wrong with it? That's generally what you'll have to do, because there's usually a lot wrong. And what's right with it? Sometimes people produce wonderful graphics. So this is a cool website to visit, and you can certainly get different ideas from this one. We'll go to this. We'll see how quickly it loads. It's pretty slow today, again, for whatever reason. So while we wait for that to load, here it comes. So these are fake news stories, right? And so it's got lots of different features that make it a graphic and some features that make it less of a graphic. So it's got a lot of text in there, right? And the text is telling you what the story's about. And what I don't know, and what isn't really evident from the graphic, is what the size of the box means, right? So what we're probably trying to do here is compare the sizes of each of these rectangles, okay? Now there's a hint as to what might be being measured here in this box. The DEA raids United States Senator, Dems in a panic, whatever, 15,800 hits. So it kind of tells you that here's a piece of news, it's had 15,800 hits. So I'm guessing that the size of the box is the number of hits. And so you can see they get bigger and bigger. Barron Trump wins National Academic Award, etc., etc. Obama and Michelle to divorce, and so on. The immigrants started wildfires. Oh my God, it's just getting worse and worse, and so on. Now, usually when you see a graphic like this, there should be something that tells you what the size represents. Here, you've got to hunt around and see what it is, okay? Which is not good. So they should at least have a legend, and they should have a title as well. Aside from that, it's okay. You can sort of see the different sizes of things. It's a bit hard to compare sizes of rectangles, particularly when they're in that sort of spatial disarray. And spatial disarray is something that we'll talk about because, when you construct statistical graphics, one of the things I mentioned yesterday is going to be really important. If you want to compare the sizes of two objects, or if you want to understand the relationship between two objects, even if size isn't what you're looking at, you're really best off having them close together. Okay? So, for example, when you're a kid, if you have a brother or a sister, you might have done this thing where you stand back to back to see who the tallest is. Who's done that? I've done that. I've done that. We do it back to back because front to front is really too hard to contemplate. Bit naughty. So you stand back to back. Why do you do that? Well, in order to tell, if it's close, in order to tell who's taller, you need to have people right side by side, and then you just look at the tops of their heads and you're hoping they're standing on level ground. Right? This is not like Tom Cruise in a movie. He always stands on a box. Did you know that? Because he's a little guy. So you stand back to back. Now, the worst way to tell if someone's taller than another person, unless it's completely obvious, is for one to stand over here and one to stand in the back corner of the room and go, which one's taller? How are you going to do that? Right? So proximity is really important from a graphical perspective. We know that, right, because we've seen bar charts. And the thing about bar charts is the bars are right next to one another. And there's a bloody good reason that's the case. You want to compare their heights. And if they're not next to one another, it's harder. If you create a bar chart where you've got big gaps between the bars, it's actually harder to tell which one's taller if it's close. If it's not close, okay, you might still be able to tell it. But them being next to one another is important. And this is why design is such an important part of graphic construction. If you use a package like Microsoft Excel, it will produce bar charts with gaps between the bars. Right? That's just the default. But that's not the right way to do things. You want to produce bar charts where the bars are right up against one another. And that's going to give you your best chance at visualising those differences. And so one of the things we're going to talk about in this course is how defaults in software really impact the way people do things. The thing about defaults is that they drive people's behaviour. People almost always just go with the default. And that's because computer programs these days are far too complex. And so the default is good enough because you don't want to have to think about how to change it. The problem with that is if defaults are poorly chosen, you don't get what you need to get. And you've got to be able to override that. Now, this is why R is such a good tool, because R gives you that ultimate control. Okay? So, when you come to class and you see me do stuff in R, you'll be cursing, right? For two reasons. The first reason is that R looks so complex. And then the second reason is that I'm going to show you all these different functions in R, and they're all going to have options with different names. It's just going to look like it was thrown together by a bunch of different people who didn't talk to each other, which is exactly how it was made. Okay? Whereas you take a program like Excel, which is all done by people who do talk to each other, all those nice guys at Microsoft, and they are mostly guys, so I can say guys, and yet you still get a mess because the defaults are chosen. Yes, the people are talking to each other, so there's a consistency about the interface, but no one ever bothered to teach them anything about visualisation or about statistics, and you know that because Microsoft Excel cannot produce a histogram. I mean, you can do a histogram in Excel using its histogram function, but what you get's not a histogram. And a histogram's pretty bloody simple, right? And it's just not done properly. And so defaults in software, they help people because they mean you don't have to think as much, but they actually ultimately ruin your day because they make your message much less effective. Okay? So here we are, spatial disarray. If I want to know how big this one is compared to something over here, okay, it's very, very hard to get any sort of fine comparison. About the only thing I know for sure is that as I scroll down the page, the boxes are getting bigger. So that looks to be the case. But comparing, this with this is really kind of hard, and they're next to one another. Comparing this one, LGBT adding P for pedosexual, I don't know, whatever. And this one, Trump revokes press credentials for 6 news outlets. These two are not next to one another and they're oriented differently. And so, again, it's just hard to tell the difference. Anyway, this is a cool website. You can spend hours on these things. I don't recommend you spend hours, but I recommend you spend minutes and have a look at a few different things and get a sense for what's out there. Now, the other website I wanted to show you was this website by Michael Friendly. So this guy's been putting together this website for a number of years now. And this is somewhat more conventional. The David McCandless website is really kind of, it's one of those websites that's trying to be sexy. So lots of colours and big lettering and all that sort of junk. He's trying to sell books, right? That's the game. Michael Friendly's not trying to sell a book. He's an academic at York University. So he's just trying to do something to teach people about visualisation. So on the left-hand side, you've got the visualisation gallery. Okay, he's got things that he calls laurels, which is good, darts, which is bad. So you can go and have a look at all these, and you can have a look at a few different things. So darts are the bad ones. So let's have a quick look at a couple of bad ones. So you go to the lie factor. All of the graphs that you have here, they're out of Tufte's book. Okay, that's where these all come from, Tufte's book. We'll have a look at this one here. It'll come up. It won't come up. Oh bugger, I've closed the entire window. Here we go, back we go. Let's see if I can get back to that. Oh, what was I looking at? Darts, yes. The lie factor. Let's see if we can get any of them to come up. No. Okay, so he's got a problem on his server. How big can I make it? Let's see how we go. Anyway, all right, you get the idea. There we are, there's the graphic. Unreadable, but can anyone tell me what kind of graphic this is? Is it a pie chart, line chart, bar chart, bar chart? It's a bar chart. But the bars are doctors, right? So welcome to the world where information and truth sits on this side and looking cool sits on this side. Smush them together. This is the sort of stuff you get. And if you look in newspapers, magazines, on the internet, almost every bar chart you see doesn't use actual bars. It uses little bears or little motorcycles or little doctors or you name it, right? And yes, it makes you look at it. And let's face it, half the reason you print a graphic is so people will look at it. So yeah, I get it. But the message is corrupted. And it's corrupted by the fact that if I look from the doctor on the left to the doctor on the right, and I ask you a simple question, how much bigger is the leftmost doctor than the rightmost doctor? What is your answer? Now there are two answers to that question, right? In a bar chart, what do you compare between two bars? Height, right? So that doctor on the left, he is about twice the height of the doctor on the right. Yes? So it's a 2-to-1 ratio. Okay. Does it look like the doctor on the left is twice as big as the doctor on the right? What do you reckon? What ratio do you reckon it looks like? 4. 4. Why 4? Because doctor got taller, but you didn't want him to look like a freak, so he got wider as well. He got twice as tall, also got twice as wide. 2 times 2, 4. So that's what Tufte calls the lie factor. So you've got a real ratio of 2-to-1, but a visual ratio of 4-to-1. And so that's a lie by a factor of 4-to-2 or 2. They're telling a big lie. Okay? So a lot of graphics suffer from this problem. Okay, the lie factor. Now let's go and have a look at another one. And I just want to talk about this graphic a little bit. I hope that I can show it. If I can't, I'll find it on Google Images. There it is. Okay. This is supposedly the best statistical graphic of all time. Okay. Now, most of you are looking a bit underwhelmed. I get it. Because these days, you look for colour and it's got to jump out at you. It's probably got to move and all that kind of stuff. This graphic was constructed in the 1800s, okay? Well before the iPhone, right? They barely had paper. No, they had paper. But this was done by a guy named Minard, a French cartographer, okay? Now, I'll tell you what's beautiful about this graphic. It tells a story. It tells the story that has actually been retold over history many, many times. Every time there's a war in Europe, they try to take Russia, okay? This just seems to be the way the world works. Now, I don't know why, because Russia's cold, they eat potatoes and beetroot. I mean, why do you want to go and take that over? But they do, right? So every war in Europe always moves to the east and tries to take Russia. So this happened in World War II, you know that. This happened to Napoleon. Napoleon, the great emperor, the guy who's always had his hand in his jacket, probably because the artist couldn't draw hands, I don't know. This tells the story of Napoleon's march on Moscow and his retreat. So, if you look at the graphic, it's got two elements. It's got this sort of tan element, and then it's got the black element. The tan element is Napoleon's army, and the width at any point is the size of the army. He started with 422,000 men, okay? And he started here. And he marched towards Moscow. Now, when you try to invade Russia, this is pre-nuclear weapons, they fight back, okay? And your army gets smaller because they kill some of you. And so you can see, as you move through time, the army of Napoleon dwindling. So you see multiple things. You see the size of the army at any moment. You see the path they took, okay? You see, for example, where some French people went in the wrong direction. That's up here. I don't know where they were going, didn't do well. Then you see someone try to outflank the Russians, okay? Went a different way. They made it to Moscow with 40,000 people. That's a lot less than they started with, 1/10, okay? Now, an accident of history was that as the French went past, the Russians adopted a scorched earth policy. They destroyed everything in behind them. And what that meant was that when the French retreated, they couldn't go out the way they came in. And that made this a better graphic, because the black part, their path out, is different to their path in. So the black line is the French retreating. Turns out, when you try to invade Russia, they fight. Turns out, when you try to leave Russia, they fight. And so the French army kept getting smaller and smaller and smaller and smaller. And there they ended up back there with fewer than 10,000 men. Most of them died. You see their path out. This graph here shows the temperature, and most of it is below zero. Freezing, right? And not nice cold like Canberra, Russian cold, right? Russian cold. So, let's think about why this might have been called the greatest graphic of all time. First of all, it tells a story. Remember what I said to you? Graphics have to be based on something interesting, something substantial. Don't produce a bar chart that's bullshit, right? You can go to the annual reports of big companies. I saw the most hideous graphic. It was the annual report of a company, and it had a graph labelled turnover in 2016, which was a bar chart, which had one bar, which was the turnover in 2016, and that was the whole chart. It took up a whole page of the annual report. What the? Right? That is just pointless. What a waste of ink, what a waste of paper. And what story does it tell? Well, okay, you can read the number, but you could read the number without seeing the bar, and the height of the bar had better be proportional to that number because there's just one bar, right? So completely useless. And I've seen that published in a glossy annual report, okay? No story. This has a story. In fact, this story is about life and death, right? These French soldiers died as they went in and came out of Moscow. Second, it carries with it information about time, information about temperature, information about army size, information about location. And let me tell you, this was before Google Maps, a long way before Google Maps, right? So all of this information would have been gathered painstakingly at the battlefront. This isn't stuff like data is gathered these days. Like, this would have been reports back from the front, okay? And that's why it's a brilliant graphic. So I wanted to show you that, just to show you that not all the graphics that we're going to look at in this course are modern, colourful, snazzy. This is a graphic that's probably going to stand the test of time and be regarded as the greatest graphic for a lot of time yet to come. And so it's kind of the gold standard. So I know we spend a lot of time talking about these things, but here's the thing. When you come out of this class, you need to be able to do two things. You need to be able to take data and create graphics. But more importantly, you've got to be an advocate for good communication to those around you. You are lucky to be able to come and hear about how to communicate well. So many people never learn that lesson. Now, here's a story that I think is worth telling, even though it makes it sound like I've got a big head. But I've been teaching this course for 25 years, maybe. Every year, in fact, just 3 days ago, I get emails from students who graduated 10, 15 years ago. And they always start with, "Hi Michael, you probably don't remember me, but I just saw something at work today that made me think of you." And then they send me some graphic that came across their desk at work. And they say, "This is the kind of rubbish that's been put on my desk and I'm going to fix it." Right? And that's where, genuinely, you start to make a difference. Okay? If I could hook into the modern zeitgeist, right, you know that every day these days all you hear about is fake news. You know what drives fake news? And it's not Trump, right? He just says it a lot. But what drives fake news is a fundamental inability to stay informed. If everybody was informed, there'd be no fake news because you'd sniff it out in a heartbeat, right? Being informed and having an informed citizenry is the hallmark of civilization. And you know, we're headed in the wrong direction, folks, at the moment. So our only hope is for communication to get better, more accurate, more honest. And you don't want to be making mistakes around this. And that's why this stuff's so important. So, that's why we talk about it. So yes, it's a stats course. And look, I could stand here and talk to you for 39 hours in a semester and only type R commands. You would probably be bored out of your head. But I think it's important to communicate the bigger message around why statistics matters. Okay? And it's not just about being able to use R. It's about being able fundamentally to communicate information and help inform people. Anyway, I can absolutely recommend this website. Again, as you search for graphics, I expect you'll find graphics from anywhere and everywhere. It absolutely astonishes me every year the variety of graphics that get handed in at the end from anywhere. And I'll show you some real life examples. I collect them, some of which will curl your hair, right? For different reasons. So start by looking at this page. Usually once people see this page, they always ask me, "Oh, can I use an example off this page?" The answer is you do whatever you want, but if you can't find something different and better than what's on this page, you ain't looking, and I want you to look. So these pages that I show you are really designed to inspire you to just keep your eyes open, and if you look around, you'll see this stuff everywhere. So, all right, so that's enough fun for today. I know we've spent a lot of time on that, but it's worth it. Okay, back to R. So we're going to start, by the way, today we're going to start on chapter 2 for those who are following along in the notes. So I'll start talking about that in a second. But before I get to that, I just want to take you through one more example of graphics in R and show you a couple of different things. So this is a data set that's in the class data. It's called Anscombe. Anscombe is the name of a statistician who was at, where was he? Yale, I think. And he came up with these data sets, right? So you've got x1, y1, x2, y2, x3, y3, x4, y4. So you've got 4 pairs of xy variables. Okay? Now if I attach Anscombe is a data frame, so when I attach it, I can refer to its columns by name, right? So let me just show you something. I'm going to fit a linear model. Whoops, I'm not typing in the right spot. Let me go down here. I'm going to fit a linear model, y1 tilde x1. So all this does is fit a straight line model between y1 and x1. And that tells me that if you do that, the model is y1 is 3 plus a half times x1. Okay? So I'm going to call that model 1. So I'm going to do that for all 4. So model 1 is lm y1 tilde x1. Okay, people always ask me where's the tilde key as well. This is after they've asked me where the escape key is. Guess what? It's right under the escape key. So there you go. I guess people don't use the tilde key very often in real life, right? Because who types tilde? But anyway, model 2, if you use R, you type it. y2 tilde x2. Model 3 is lm y3 tilde x3. And model 4 equals lm y4 tilde x4. Okay, so I've just fit linear models to each of those 4 data sets. Okay, now you might not have seen LM before. LM fits linear models. The syntax is you put the y variable here, you put a tilde, and then you put the x variable here. The tilde is a binary operator which says basically relate this to this using the model specified by the function. So if you're using LM, it says relate x1 to y1 in a linear model. Fit a straight line. But you can fit, there are other kinds of models. There are GLMs and all sorts of other things, but that's what the tilde... So this is called a model notation, okay? And again, you might have seen that before, but if you haven't, that's what it means. But that's not going to bother us too much at the moment. Let's look at model 1. Model 1, y1 is 3 plus a half times x1. Let's have a look at model 2. y2 is 3 plus a half times x2. Okay, let's have a look at model 3. y3 is 3 plus a half times x3. There's a bit of rounding, but basically the same. Model 4, y4 is 3 plus a half times x4. So the same model is fit for each of those. Not only that, if I look at the ANOVA table for model 1, I get this. And if I look at the ANOVA table for model 2, I get this. And you can see they're the same. And I can do the same for model 3. And I get the same thing again. And I can do the same for model 4 and get the same thing again. If I fit linear models to these 4 data sets, the models look identical. Same fit, same ANOVA table, same error variance estimate. Everything numerical, the same. Okay? Now, what have I not done to this data? I fit all sorts of models to it. What have I not done? I haven't looked at it. Cool. So let's look at it. Okay, now to do this, I'm going to look at it all on this one screen here. So I'm going to go par mf row equals C22. What this does is it says I'm going to put multiple plots on the same screen and I'm going to lay them out in a 2x2 grid. So par mf row equals C22 will lay them out one next to the other. Okay? And I'm going to plot x1, y1 and I'm going to add a line which is the model that I just fit. Okay? So I'm doing all that in one line. You can do that if you put a semicolon in, it's like you hit carriage return. Okay? So you can do stuff all in one line if you want. And there's that first plot. So, looks all right? Straight line, pretty good. Let's do the same for x2 and y2. So I'll just space back and... Okay. What do you reckon? It's the same line. We happy? We stunned? You must be stunned. Did everyone have a big lunch? Is that what happened? Actually, I know you couldn't have had a big lunch because if you go to the pop-up village, you'd still be lining up. That's the way it is over there. All right, so what's going on in that picture? Okay, here's something we're going to do lots in this semester. Let's do it now. I want you to pull your finger out of wherever you've got it, pocket, on your book, wherever. Nice and high. Come on. Come on. Don't be embarrassed, everyone's doing it. Okay, what's the day to do? I'm watching your fingers, watching your fingers. Oh, you'll learn to play with me eventually. Okay, it's curving, right? It's curving. Straight line model, not a good model. Okay. All right, cool. Let's do the next one. X3, Y3. Okay, what's going on there? Got an outlier. Exactly. Okay? So here's the line that got fit, and here's the data, and you can sort of see it's fit the wrong line, and the reason it's fit the wrong line is that that guy up there is out of line, and he's pulling the line up towards him. Okay? So that's an example of an outlier. What about the last one? So look at the last one. X4, Y4. What's going on there? So I heard someone say another outlier. Kind of. This is not an outlier, right? This is not an outlier. You go, what the hell? It's away from all the other points. Outlier does not mean a point that's not near all the others. An outlier is a point that is a long way from the model that's fit, right? And that point's not a long way from the model that's fit. It's right on the line, okay? So it's called an influential point, an influential point. So you want to fit this line, right? The one that goes more or less straight up. This point over here is influential and it levers the line all the way around. So it's called an influential point, okay? So you can think of the difference between an outlier and an influential point a bit like you think of the difference between a criminal and a politician, right? They're both doing bad things, but the politician has influence, okay? So that's kind of how it works. Now, what's the point of showing you this? 2 points. I wanted to show you how to get multiple plots on a single page. That's something we're going to do. And the reason we're going to do it is that, as I said to you earlier, having things next to one another is a really powerful promotion of comparison. And comparison is the lifeblood of communication. Every graph you see should have you asking the question, compared to what? What am I comparing on this graph? And that's why a bar chart with one bar is a stupid graph, because it doesn't ask you to compare anything to anything. Okay? So compared to what is the question you should always be asking. The second point of showing you this is that you cannot afford to go on autopilot when you look at data. You can't just fit models and hope that the data does what you think the model says it does, because this shows you very dramatically that that ain't the case in a really simple context. And this is XY data, right? 1X, 1Y. This can be visualised, right? Because it's two-dimensional and we've got paper or screen, which is a two-dimensional surface. Now, here's the curse of the modern age. Data is now hideously high-dimensional, right? We don't get data sets with 1X and 1Y anymore. We get data with 1 million X's, right? And then we say fit models to it. And so you can see why people just push the button and hope for the best, because visualisation is hard. But, you know, this simple example tells you that if you don't visualise it, you deserve what you get, which will generally be a bad model, okay? So visualisation is really critical, and it's even more critical now that we live in this ultra-high dimensional world where nothing happens with just 1X and 1Y anymore, okay? Having said that, we are going to spend an awful lot of the semester talking about 1X and 1Y, because you've got to start somewhere. But in the end, it's going to be about what do you do in high dimensions. So a big focus that we're going to have this semester is dimension reduction. How do you get things down to a manageable level? So we'll be talking about that. Okay, so let's move and talk about, just going to dive back onto Waddle here. And I'm going to take you through the start of chapter 2. So every chapter is going to be like this. We're going to focus on a single data set, which we'll get very used to for a little while. Every data set has a story, and we're going to talk about the story. Because like I said, if you don't have a story, you shouldn't be talking about it, okay? And we're going to go right back to basics, okay? So for those of you who've only ever done one statistics course, you can kind of say, oh, okay, this is cool. We're going to talk about things like histograms and that kind of stuff, right? And you might be sitting there going, I know all about histograms, so I'm cool. Well, what I hope is that in a couple of weeks' time, you will think to yourself, you know, I probably didn't know as much about histograms as I thought I did, and I hope you'll be thinking fundamentally differently about these tools, okay? So we're not going to think about just plopping a histogram on the page and moving on. We're going to think about what makes a histogram good, what makes it bad, what makes it effective, and what choices you make when you construct it that govern those things, okay? So this is really a looking under the hood exercise, okay? So, you know, you go home and say to your mum or dad, I'm doing a third year class and we're talking about histograms, they might, you know, contact the ANU and say, we're not paying, because shouldn't you be doing that in first year? But the answer is no, we're talking about construction here. We're not talking about the histogram itself. We're thinking about the principles that go underneath it. All right, as I said, there's a story to everything, and here's the story. By the way, so who's been looking up in the sky recently? What? Who didn't look up in the sky last Saturday morning at 5:30 a.m? You really missed out. Man, blood moon. Blood moon. Up in the sky, the moon went red, then it more or less disappeared, then it went below the horizon, where I imagine it went red again. The shadow of the Earth moved across it. Okay, the moon's up in the sky. Right next to the moon, in the sky, this big, bright, red light, Mars. Do you know you're not going to see that again for 100 years? So you did miss out big time, right? Anyway, go outside tonight, find Mars in the sky. You can't miss it. It is the biggest, brightest light in the sky at night. It is currently at its closest point to Earth that it will be in a very long time, okay? And don't miss these opportunities, because I went out for my wife and I normally go running at 5:30 in the morning, but I woke my wife up and I said, come outside and just go for a 10-minute walk with me before I go for my run. You've got to live this with me, because we ain't seeing this for 100 years and we'll be dead before that. So we did. We walked around our neighbourhood in the dark, holding hands. It was very romantic, and looking at the moon. Right? It was cool. So you missed out. So there's something about the universe that excites us. We don't know why, right? I mean, we live most of our lives buried in our phones like this, but then there's this universe. And as far as we know, asterisk, we are it as far as life is concerned, right? Certainly intelligent life, although I have heard people say in response to that, you call this intelligent, and that's fair enough. So this is a story about the galaxy, okay? And it's a story about stars, and it's a story about the way our galaxy looks. So most of you would know that our galaxy is a disk galaxy. It's got big spiral arms. We're out in one sort of little corner of it, okay? If you do go outside tonight and look up into the sky, if it's a dark night, you will see more stars than you can count, and every single one of those stars could have a planet just like Earth, with people just like you, listening to someone just like me. If they're that lucky, right? So, how did this all happen? Well, we don't know. We don't know. But what we do know is that gravity works, and that gravity takes heavier elements and sucks them towards each other. And we know that as galaxies form, the heavier elements are going to be sucked into the centre and the lighter elements are going to stay outside. And when galaxies first form, they start as big spheres, and then as gravity takes its effect, they flatten because the heavy elements come in towards the middle, and then the thing starts to rotate, and you end up with this big sort of disk with everything rotating around its centre, and the sphere, it still has billions of stars in it, but many fewer of them live on the disk. So that's what we think happens with galaxies. Now, you know, the most amazing thing about this is we know this. How the hell do we know this? Because we have not been to any of these galaxies. We have not even been outside our own solar system, which is one star, right? And yet we know all of this. So we got telescopes and we got all sorts of other tools, and our Vice-Chancellor has a Nobel Prize, you all know that. And he does this stuff for a living. And I just get excited about it because I can go for a romantic walk on a Saturday morning with my wife, which is cool. Okay, so this is what this story is about. Now you might say, why is he telling us such a story? Well, I want you to get interested in this because you might look at this story and you go, oh, it's pretty dull. Yeah, stars collapse into the middle, they rotate around the disk, yeah. But when you think about it, it is really fundamental to the way we came to be. You yourself are a collection of atoms. And the question of how they managed to get together and be you is really kind of special. And it all starts with the formation of galaxies. So that's what we're going to talk about. So, we're going to talk about three different types of stars. We're going to talk about disk stars. These are the stars that are on the disk. They're mainly heavier elements. Then we're going to talk about halo stars. They're the stars that are out on the outer part of the sphere. They tend to be lighter elements. And then we've got some that are in the middle. And we don't really classify them as either disk or halo. We're going to call them intermediate stars. So, people, like the people out at Stromlo, gather data. And what they did was they measured the velocity of stars perpendicular to the galactic plane. Okay? And what they're going to do is they're going to try and classify stars as disk, intermediate or halo, depending on their velocities. And so this particular study was interested in looking at the distribution of velocities of stars in each group. And that's where this data set comes from. Okay? So, let's hop on into R. So the data is here. Now, where all this data is on Wattle is if you go into what I call the computing notes for each chapter, you'll see all of these R commands. So these are the scripts for the R commands that I'm going to be following. I'm going to try and copy and paste mostly because you don't really want to watch me type. And so for this particular data set, the data's not in the class data. I'm just going to enter it in here like this. So I'm just going to copy and paste this stuff. Oh, and then try to control my mouse if I can. So I just want to get these. So there's my data. Okay, now, to begin with, we're going to start by just looking at one of these three groups. We're going to look at the intermediate stars first. So the intermediate star data is that third column. It's called inter. And if I type inter, I get this. So 0 means that it's not moving with respect to the galactic plane vertically. Okay, 45 means it's moving up in that direction. 29 means it's moving in the other direction. Okay, so you've sort of got pluses and minuses depending on whether it's up or down compared to the galactic plane. Okay. All right, let's have a look. So what's the first thing a statistician does when they look at data? They go, well, what's the mean of inter? Minus 15. Okay, so the average is minus 15, which is minus not much. Okay, what's the range of inter? They go anywhere between minus 286 and plus 117. You notice how unsatisfying this is? The square root of the variance of inter, which is the standard deviation is 87. So there's some numerical summaries of this data set. Like I said, it's unsatisfying because you really have no idea what this thing looks like as yet. Okay? So we're going to move towards ways in which we can think about this data. Now, I'm going to show you a very simple way to look at it. And that's to do this. This is called a one-dimensional scatter plot. Okay? Oh, now, notice what happened. See how it's put that graph in the upper right corner? Because I'm still trying to put 4 plots on the page. How do you tell it to stop doing that? This is what you do. You say, stop doing that. So you click the little broom. It clears it all out, clears out all of that junk, and then I can redo. Okay, so if I do it again, we get that. So this is now the velocity. This is a one-dimensional scatter plot. All I'm doing is I'm plotting the data against 0, and you can see them line up. Okay? Okay, so as a graphic, what does this tell us? Well, you can sort of see it's sparse out to the left-hand side here, and then you can see that the points start to accumulate up in this side here, and then there's a bit of a tail on the right-hand side. Okay? That's what we can tell so far. And I can relate each of those dots to a velocity by looking at the scale at the bottom. So I know that that guy here is around minus 300, and I know that the top guy's around plus 100. Okay? And I know they're sort of clumped here, and they're kind of dispersed out there. Okay? All right, so this isn't a particularly effective graphic, but there's a couple of things we can do to immediately improve it. Right? The first thing we could do to improve it is fix up its aspect ratio. See how far this scale is from the actual data? So for you to know what velocity each point goes with, you've kind of got to take your eye, push it down the page to the bottom, by which time you've forgotten what you were looking at before. So we want to change the aspect ratio to do that. Now there are two ways to do this in R. One is very complicated and one is really simple. So I'm going to show you the complicated one first. So I'm going to go par brackets dollars pin. So par are all the graphics parameters. Pin is the size of the plot in inches. It tells me that the graphic is 5.98 inches wide and 5.2 inches high. So if I say par pin equals C 5.98, but then I make it less high, I might make it, I don't know, 1, and do that, and then I redo my graphic. See how it sucks it in? Okay, so that's the hard way to do it. That's how you'd have to do it in base R. Okay? All right? So let's scrub that. By the way, just because I can do something the hard way doesn't mean you have to. I'm just showing you. So don't worry, you're not going to have to do that in real life. So I've scrubbed that. Let's go back and put that plot back on the page, back the way it was. Want to see the easy way to do it? This is why we're using RStudio, by the way. This is the easy way to do it. You move your mouse up here, you grab the edge, if you can. Come on. Ah. I want to grab the edge. Right? So you can drag it around. So that's pretty cool, right? So yeah, hard way, easy way. So by the way, you have to be using RStudio to do that. Right? If you're using base R, that won't work. You can change the window size however you want, nothing will fix it. But in RStudio, the graphical user interface finesses all that stuff. So that's pretty cool. And you can sort of see the benefit because immediately the data is close to, and remember, proximity is one of the things we care about, it's close to the scale. And you can make it as close as you like. One thing you will notice is if you make it too narrow and R decides that it can't fit various things in, you'll get an error message. Figure margin's too large. Okay? So if you ever see that error message, it just means your window's too small. And look, this bites people sometimes because you're on a laptop that's already got a small window. Sometimes you'll try to put a plot on the page and you'll always get that error because you can't make the window big enough. So if that happens to you, I share your pain. But there's not a whole lot I can do about it. Okay, what's one of the other difficulties with this? One of the other difficulties is we know there's a bunch of points in here, but you can't really see how many because they're all over on top of one another, right? So one technique that people have come up with to try to fix this is to say, okay, I've got a two-dimensional plot here. I'm going to actually use the second dimension. And I'm going to do what's called jittering. So instead of having everything sit on that baseline at 0, I'm going to just randomly pop them up a little bit. So just plot, instead of plotting against 0, plot against a random number. Now, again, I don't necessarily think this is a great idea, but it is one way. It is one way people have tried to deal with this problem. Okay, so let's try and do that.